We often take our planet for granted, but have you ever stopped to consider how much it weighs? This might seem like a strange question, but understanding the Earth's weight is a crucial part of our understanding of the universe. The weight of our planet is not just about a number. It's a key piece in the cosmic puzzle that helps us comprehend our place in the vast expanse of space. But let's clarify one thing. When we talk about Earth's weight, what we're really referring to is its mass. Weight is a force that depends on gravity, while mass is a measure of the amount of matter something contains, and Earth, as it turns out, contains a lot of matter. In this exploration, we'll delve into the weighty matter of Earth and its significance. We'll lift the veil on how scientists measure the mass of our planet and reveal the mind-blowing figures that come with it. We'll also examine how the Earth's mass is unevenly distributed and how this affects everything from gravity to geophysical processes. Furthermore, we'll discuss how Earth's mass influences the orbits of celestial bodies, including our very own moon. We'll explore hypothetical scenarios of how Earth's weight would change in different gravitational environments, and touch upon the weight of Earth's atmosphere and how it contributes to the overall mass. In addition, we'll delve into the gravitational interactions between Earth and other celestial bodies, and how phenomena like tidal forces connect to Earth's mass. We'll discuss factors that can influence changes in Earth's mass, from meteorite impacts to human activities. So let's embark on this weighty adventure to uncover the secrets of Earth's mass. As we journey through these complex concepts, we'll discover that our planet's weight is much more than just a number. It's a testament to the intricate and fascinating workings of our universe. Before we dive in, it's crucial to understand the difference between mass and weight. You see, these two terms are often used interchangeably in everyday conversation, but in the scientific community, they have distinct meanings. Mass refers to the amount of matter in an object, and it remains constant no matter where in the universe that object is. On the other hand, weight is the force that gravity exerts on an object's mass. So in essence, weight is dependent on gravity. To illustrate this, imagine you're holding a rock. On Earth, that rock has a certain weight because of Earth's gravity, but if you were to take that same rock to the moon, its weight would be less due to the moon's weaker gravity. However, the rock's mass, the amount of matter it contains, would remain the same whether it's on Earth, the moon, or floating in the vacuum of space. So when we discuss the weight of the Earth, what we're actually talking about is its mass. We're referring to the vast amount of matter that makes up our planet, from the deepest ocean trench to the highest mountain peak. We're talking about every grain of sand, every drop of water, and every living creature that calls Earth home. That's right, when we talk about Earth's weight, we're actually referring to its mass. Now that we've got that fundamental difference clear, let's delve deeper into the topic. So how do scientists measure something as colossal as our planet? You might be thinking it involves some sort of gargantuan scale or perhaps a colossal tape measure, but as it turns out, the reality is far less tangible and yet infinitely more fascinating. This Herculean task is accomplished through the power of physics, and more specifically, the concept of gravitational attraction. Now, gravitational attraction might sound like a fancy term, but the idea is relatively simple. Every object in the universe, no matter how small or large, exerts a gravitational pull on every other object. This force of attraction is directly proportional to the mass of the objects and inversely proportional to the square of the distance between them. This is known as Newton's law of universal gravitation, and it's this principle that allows us to measure the mass of our planet. To measure the Earth's mass, scientists observe the effect of its gravitational pull on objects of known mass. This is usually done by observing the orbits of satellites and celestial bodies around the Earth. By analyzing the speed and path of these objects, it's possible to calculate the mass of the Earth. But here's the truly mind-boggling part. The Earth is so massive that its gravitational pull not only affects objects in its immediate vicinity, but also objects millions of miles away. So in a way, we're all constantly feeling the weight of the world. And that weight is a staggering 5.972 times 10 to the 24th power kilograms. So the next time you're feeling weighed down, remember, it's not just you. We're all in this together under the influence of Earth's immense gravitational pull. Whether we're standing on the highest mountain peak or diving to the deepest ocean trench, we're all subject to the same fundamental force of nature, and it's this force, this gravitational attraction, that allows us to measure the mass of our planet. Believe it or not, it's all about the gravitational pull. Prepare to be amazed by the sheer mass of our planet. You see, Earth isn't just some lightweight floating around in the universe. It's packing a considerable amount of mass. In fact, if we were to put a number on it, Earth's mass is roughly 5.972 sextillion kilograms. That's a 5 followed by 24 zeros, folks. Now, that's a number that's hard to wrap your head around, isn't it? Let's try to bring it down to Earth a bit, shall we? Consider this. The average car weighs about 1.5 tons. If you were to stack cars until you reach the Earth's mass, you would need a traffic jam that stretches not just around the Earth, but all the way to the sun. And back. Over 400 times. Or let's think bigger. The Great Pyramid of Giza, one of the heaviest structures humans have ever built, weighs about 6 million tons. You'd need close to 1 quintillion, that's a 1 followed by 18 zeros, of these pyramids to equal the mass of Earth. Now, if we were to compare our home planet to our neighbors in the solar system, Earth has a mass that's over 81 times that of our moon. It's also over 300 times less massive than the gas giant Jupiter, the heavyweight of our solar system. And speaking of heavyweights, if we were to compare Earth to the Sun, well, we're just a featherweight in that match. The Sun's mass is over 330,000 times that of Earth. That's right, our home planet is just a tiny blip compared to the gargantuan star that keeps us warm and gives us light. In the grand scheme of things, Earth might seem insignificant, but it's our mass that gives us gravity, holds our atmosphere, and keeps us firmly grounded. Yes, our Earth is truly a heavyweight champion. The Earth's mass isn't neatly packed into a perfect sphere, it's unevenly distributed. This might sound surprising, but it's simply a part of the fascinating world we inhabit. Imagine a baker trying to evenly distribute raisins in a dough. No matter how much effort is put in, some parts of the dough will invariably have more raisins than others. Similarly, Earth's mass is spread in a somewhat haphazard manner. The denser parts of our planet, like the iron-rich core, hold more mass compared to the less dense regions such as the Earth's crust. This uneven mass distribution creates areas with varying gravitational pulls, leading to fascinating geophysical phenomena. For instance, the gravitational force at the poles is slightly stronger than at the equator due to Earth's oblate shape. This might not affect our daily lives much, but it plays a significant role in shaping the Earth as we know it. From influencing ocean tides to even the movement of tectonic plates, this uneven distribution of mass has wide-ranging impacts. Interestingly, this uneven mass distribution also contributes to the lumpy gravitational field of Earth, which can subtly influence the orbits of satellites and other celestial bodies. So, Earth's uneven mass distribution contributes to the unique gravitational quirks we experience. Now, isn't that a weighty thought to ponder? Our planet's mass doesn't just sit there, it influences the cosmic ballet of celestial bodies. This is particularly evident in the orbits of objects around the Earth, from satellites to the moon. Now, let's dive into the science behind this. The Earth's mass works like a cosmic anchor, generating a gravitational field that pulls objects towards it. This is the same force that keeps us grounded and prevents us from floating off into space. In the context of orbits, this gravitational pull doesn't just attract objects to the Earth, it also influences their paths. That's right, the Earth's mass plays a significant role in shaping orbits. Consider our moon, for example. Its orbit around Earth isn't a perfect circle, but an ellipse. This elliptical orbit is a result of the gravitational forces at play between the Earth and the moon. The Earth's mass being significantly larger essentially tugs the moon along its orbit, keeping it in check. Similarly, satellites follow paths dictated by the Earth's gravity. Their orbits, whether geostationary or polar, are dependent on the Earth's mass. Geostationary satellites, for instance, need to maintain a specific altitude and speed to stay locked over a certain location on Earth. This delicate balance is achieved by carefully considering the Earth's gravitational pull, which is directly linked to its mass. The Earth's mass also influences the orbits of other celestial bodies, such as asteroids and comets. When these objects come close to our planet, their trajectories can be altered by the Earth's gravitational field. This is why some asteroids initially headed for a close encounter with Earth often end up having their courses corrected, sparing us a potentially catastrophic event. This cosmic tug-of-war between the Earth's mass and the celestial bodies around us is a constant dance, with the Earth leading the way. The orbits we see in the night sky are a testament to the colossal mass of our planet and its gravitational prowess. Indeed, Earth's mass shapes the cosmic dance around us. If you've ever wondered how much the Earth would weigh in space, you're not alone. This intriguing question has captivated scientists and curious minds alike, but to answer this, we first need to remember that weight is not a fixed attribute. It's a force that depends on the pull of gravity. Consider this. You'd feel lighter on the moon than you do here on Earth, not because your mass changes, but because the moon's gravity is only about 1/6 of Earth's. Now, if we apply this concept to our planet, the Earth's weight would also change based on where it's located in the cosmos. In the vast expanse of space, far from any celestial bodies, Earth would be weightless. Yes, weightless, because weight requires gravity. And in the deep void of space, there's no significant gravity to speak of. But what if Earth were placed near a massive celestial body, like Jupiter or the Sun? In this hypothetical scenario, the gravitational pull of these larger bodies would exert a force on Earth, giving it a weight. And that weight would be colossal. After all, the Sun's gravity is about 28 times stronger than Earth's, while Jupiter's is over 2.5 times stronger. But let's not forget that Earth itself exerts a gravitational pull. Even in the vastness of space, Earth would still pull smaller objects towards it, giving them weight. So, in a way, Earth would still have a kind of weight in space, depending on your perspective. The fascinating reality is that Earth's weight isn't a fixed number. It's a dynamic quantity that changes based on its location and the gravitational forces at play. This not only challenges our everyday understanding of weight, but also underscores the incredible complexity of our universe. So Earth's weight changes based on where it's located in space. It's not just the land and water that contribute to Earth's mass. Our atmosphere plays a part too. You might be surprised to learn that our atmosphere, that vast expanse of gases enveloping us, is a significant part of Earth's weight. Let's break it down. Our atmosphere is made up of layers of gases, primarily nitrogen and oxygen, with a sprinkling of other elements. These gases, although seemingly weightless as we breathe them in, actually exert a force downwards due to gravity. This is how we get atmospheric pressure. Now, when you add up all that pressure exerted by the entire atmosphere, you get a rather hefty number. So, while the atmosphere might seem light and airy, it has real weight. It's a reminder that even the invisible elements around us play a significant role in the grand scheme of things. So, the next time you take a breath, remember, you're taking in a tiny piece of Earth's weight. Indeed, even the air around us adds to Earth's weight. Our planet doesn't exist in isolation. It's constantly interacting with other celestial bodies. You see, Earth, like a social butterfly, is incessantly flirting with its celestial neighbors. This interaction is not just on a superficial level, but it's a deep gravitational one. It's all about the give and take of forces, the ebb and flow of energy, the push and pull of attraction. Picture this. The moon, our closest celestial buddy, is about 238,000 miles away. A long-distance relationship, if you will. Now the Earth's mass exerts a gravitational pull on the moon, keeping it in orbit. But the moon, though smaller, also has a gravitational pull of its own. This pull from the moon is what causes the rise and fall of ocean tides on Earth. And it's not just the moon. The Earth is also engaged in a gravitational dance with the sun, which is about 93 million miles away. Despite the distance, the sun's massive gravitational pull keeps Earth in its orbit, and in turn, Earth's gravity affects the sun slightly. But there's more to these interactions than just orbits and tides. They also affect Earth's shape. The gravitational pull from the sun and the moon creates a slight bulge at the Earth's equator. This bulge is why Earth is not a perfect sphere, but an oblate spheroid. Even distant celestial bodies have a role to play. For example, Jupiter, the largest planet in our solar system, has a gravitational influence on Earth. Although this influence is minute, it's significant enough to cause small variations in Earth's orbit over thousands of years. So it's clear that Earth's mass doesn't just sit there. It reaches out, it pulls, it shapes, and it moves. It's a dynamic player in the cosmic dance of the universe, constantly interacting with other celestial bodies, influencing them and being influenced by them. So Earth's mass influences and is influenced by other celestial bodies. The Earth is not static, its mass changes over time due to various factors. Just as we humans are always changing, evolving, and adapting, so too is our planet. The Earth's mass isn't a fixed entity, frozen in time. Quite the contrary, it's an ever-changing figure influenced by a myriad of factors, some of which may surprise you. Meteorite impacts, for instance, add mass to our planet. Every year, tens of thousands of meteorites, small fragments of asteroids or comets, make their way to Earth from space. While many of these space rocks are tiny, their cumulative mass can add up over time. But it's not just about addition, loss plays a significant role too. The Earth loses mass through the escape of gases from our atmosphere into space. Hydrogen and helium, the lightest elements, can reach escape velocity and drift off into the cosmos. And then there's the process of accretion. This is the gradual growth of a body, like the Earth, by the accumulation of matter over time. The Earth continues to accrete dust and particles from space, again altering its mass bit by bit. But let's not forget the most dramatic loss and gain mass events that can occur. Massive volcanic eruptions and large asteroid impacts. These rare but significant events can cause a noticeable shift in Earth's mass, even if only temporarily. And what about the human impact? While our actions may seem insignificant on a planetary scale, human activities like mining and construction can redistribute mass within the Earth, potentially causing tiny changes in the Earth's rotational axis and length of day. In conclusion, our Earth is a dynamic and ever-changing entity. It's not just a static sphere floating in space, but a living, breathing planet with a mass that fluctuates due to a mix of natural and human-induced factors. So, the next time you step on a scale, remember that the weight you see is influenced by a planet that's continually changing beneath your feet. Yes, even our planet's weight isn't constant. We humans have a profound impact on our planet, but can we influence its weight? This question might seem a bit outlandish, but let's delve into it. When we think about human activities such as mining or construction, we're essentially moving materials from one place to another. However, it's crucial to remember that we're not introducing or removing substances from the Earth. We're simply redistributing what's already there. Consider this. When we mine for gold, we extract it from deep within the Earth and bring it to the surface. But the mass of the Earth remains unchanged because the gold was already part of it. Similarly, when we build skyscrapers, we're simply reorganizing materials, not adding to the Earth's mass. But what about launching rockets into space, you ask? Well, that does technically reduce Earth's mass, but by an incredibly tiny amount. In the grand scheme of things, our activities have a negligible impact on Earth's weight, so even our actions can subtly affect Earth's mass. We've explored the fascinating world of Earth's weight, from its staggering statistics to its dynamic changes. We've delved into the fundamental difference between mass and weight, and how this applies to our home planet. We've grappled with the Herculean task of measuring Earth's mass and marveled at the mind-blowing statistics that come from this endeavor. We've journeyed through the uneven distribution of Earth's mass and how this variance influences everything from gravitational pull to geophysical processes. We've contemplated how Earth's mass dictates the orbits of celestial bodies and considered what our planet's weight might be in different gravitational environments. We've even pondered the weight of our atmosphere and how it contributes to the overall mass of Earth. We've examined the dynamic nature of Earth's mass, how it interacts with other celestial bodies, and the impact we humans have on it. Remember, our Earth is a heavyweight champion in a cosmic dance, influencing and being influenced by the universe around us.